You're listening to Skeptoid. I'm Brian Dunning from Skeptoid.com. How do homing pigeons navigate? When I was a teen, we had a flock of homing pigeons. Often we'd travel somewhere by car and we'd take a box of them with us and release them, and it was not uncommon to do this as far away as 50 or 100 kilometers. They nearly always beat us home, though sometimes a few of them took a bit longer, sometimes even a few days. But I don't think one of them ever failed to make it back. And of course, my experience is hardly unique. Homing pigeons have been used for communication, sport, and even delivery for as long as 3,000 years, according to some sources. How do they do it? Their ability to return to their home after lengthy travel is one of the great mysteries of the animal kingdom. Today, we'll look at what we've figured out so far. To start with, I have to disabuse you of the notion that many of you are screaming right now that they navigate magnetically, using some sort of biological compass attuned to the Earth's magnetic field. This explanation is almost always the first one given by most sources, including reliable sources, without critique. But although some data does support this, plenty of data does not. In all likelihood, pigeons use a combination of senses. No data exists proving a single mechanism. Homing pigeons are a variety of the common rock pigeon that have been selectively bred over the centuries for their homing ability. But keep an important fact in mind. Many bird species do something very similar, migrating seasonally between winter feeding grounds and their mating sites, often to the very same place they were hatched. So although we're focusing on pigeons, remember, this is a widespread avian trait. When released, pigeons fly up into the air, where they usually circle for some time. A few birds will immediately head in a beeline straight home, impressively taking the as the crow flies line, rather than following the considerably more complicated ground journey with all its turns and detours. Some will ultimately head off in the wrong direction, but most will gain the correct bearings soon. Some will roost locally for perhaps a day or two, and finally head off in some direction. About half the birds will travel in small groups. How many will ultimately make it back to their home, and by home we mean the specific coop where they live and eat and sleep, depends on the distance. Most or all will return in journeys of up to 100 kilometers, and about half will return from journeys over 200 kilometers. How do they do it? The number of senses they engage, and the number of influences that might disrupt their ability, are both surprising. Let's review some of these senses. First, visual. When released from the same location, pigeons will learn a preferred route and stick to it, even if it's not a straight line. These routes appear to be learned and followed visually. Such routes tend to follow major geological features and linear features like roads and rivers. Urban landscapes are typically most difficult for them to learn. This use of visual navigation for familiar places and familiar routes is widely accepted, and certainly one of the pigeon's most important tools. But when they're far from home or in an unfamiliar place, we've found that they still use eyesight to follow the sun. A number of studies in the 1980s found that pigeons learn about how the sun moves across the sky during the first months of their lives, and are thus able to use its position to judge general directions. But at best, it's only a partial solution. Knowing your direction is not the same as knowing your location, and thus which direction you need to go. But there are some theories for how pigeons do this. Gravity. One of the more controversial proposals is that pigeons and some other birds may use gravity maps to orient themselves. A few researchers have been pursuing this hypothesis for a long time. Recently, a study was published presenting the hypothesis that pigeons have some type of biological gyroscope that remains stable throughout their lives, and which is calibrated to their home. Thus, whenever they move to a new location on the spherical Earth, the gravity vector differs from that stored in their internal gyroscope. Were this to be the case, gravity anomalies, which are found all over the world, would interfere with their homing ability, And this is what happened when the researchers took pigeons into a known anomaly inside an ancient meteorite impact site in the Ukraine. Pigeons who had to deal with the anomalous gravity had more difficulty homing than control pigeons outside the anomaly. Sounds sketchy? It was a very small-scale experiment, and the effect appears to have been equally small, and so far as I could find, it has not been replicated. If there's anything to this hypothesis, it probably needs a lot more supporting data. Okay, auditory. Nobody seems to have figured much about how pigeons might use hearing to navigate, but there is some evidence that shows certain sounds can disrupt their ability to home. Research published in 2000 studied 4 pigeon races in which large numbers of birds were lost or delayed upon encountering sonic booms from the Concorde flights. Several researchers have also found correlations between homing ability and infrasound, extremely low-frequency audio traveling a long distance and coming from various sources, including the ocean. One paper, noting seasonal variances in pigeon homing abilities in the Northern Hemisphere, proposed linking this to seasonal storms over the North Atlantic, said to produce long-distance infrasound. Supposedly, they learned to build an infrasound-based map of the area. It's a bit of a wild hypothesis, and, so far as I could find, has not been largely replicated. But it does offer a glimpse into the breadth of different types of theories researchers are proposing. Okay, here's the one you want to hear the most: magnetic. A lot of animals have various parts of their anatomy containing magnetic crystals, but few of them show any definite use. Pigeons have such crystals in their beaks and in their eyes, providing them with an inclination compass, sensing the inclination of flux lines in the Earth's magnetic field. Theoretically, this lets birds in either hemisphere discriminate between 2 directions, toward the pole and toward the equator. By equipping pigeons with small electromagnets, it's been shown that we can confuse them to some degree by changing their magnetic environment, but only on overcast days when they can't see the sun. This would suggest that magnetic navigation is used as only a backup to visual-based solar navigation. They could be similarly confused with an inverted magnetic field during transport to the release location. However, these effects were only found on very young birds and have not been widely replicated. Magnetic navigation is plausible, but at best it's only one influence the pigeons may use. As with the suggested gravity gyros, using magnetic inclination would be extraordinarily low resolution and hardly useful for navigating from place to place. Over longer distances, it becomes more plausible, but at best, it gives latitude data only. Clearly, magnetic orientation can be no more than a part of the overall picture. Olfactory. Some of the newer and more interesting discoveries in pigeon homing ability have been in the field of smell. An urban legend exists that says birds lack the sense of smell, but we now know that some birds can smell extraordinarily well. Seabirds top the list with up to 37% of their brains dedicated to the olfactory, using smell to locate food far across the ocean. Songbirds bring up the bottom of the list with as little as 3%. Pigeons have about the same number of olfactory receptor cells as humans, so we think their smelling sensitivity is about equivalent to ours. However, they have about half again as many olfactory genes, meaning they can distinguish a much greater number of different smells. We've learned 2 interesting things about homing pigeons and smell. First, that pigeons reach their destination faster on days with higher air pollution. We learned this by analyzing the results of pigeon races held in polluted areas of China. Second, we learned that pigeons deprived of their sense of smell are unable to find their way home at all. In a model called the olfactory navigation hypothesis, pigeons spending most of their time at home learn the various smells brought in by the wind from different directions and develop a sort of odor map of the region. One interpretation of this data is that the greater availability of smelly cues on a day with high pollution gives them more data with which to read their odor map, so they find their way home more easily and thus faster. Seasonal variances in their homing ability also correlate very well with blooming seasons. Olfactory navigation appears to be the model with the most and best data. By no means is it conclusive, but it's probably safe to say that smell is likely the most significant sense employed by homing pigeons finding their way. We know that vision also plays an important role, especially in following familiar routes. Other senses may also play some role, but we can't say how much. Age. Perhaps the most significant factor that confounds a pigeon's ability to home is its age. Young pigeons have a much harder time making it back than older and more experienced ones. This strongly suggests that the ability is not simply innate, as many people think, but is based on a technique that must be practiced and learned. Pigeons less than 3 years old who make it back to their homes almost always do so in the company of more experienced pigeons, over 3 years old. Okay, to summarize, sight and smell are probably the most important tools the pigeons use, and some of the other senses discussed probably also contribute. They use what we call a multifactorial navigation system, based on multiple types of input. It requires practice and experience to use well. It is complicated and does not rely on the single magic bullet of some mysterious animal ability that appeals to our native tendency toward the naturalistic fallacy. One other thing we can say that biological compasses reading the Earth's magnetic field are certainly not pigeons' most important mechanism, and may in fact play no role at all. I will end this episode with one of my usual admonitions. Next time you see an article in the news saying that the mystery of how birds navigate has finally been solved, please do not email it to me and say, "Hey, look, it's been solved." Instead, carefully read the original research the article is talking about, or read what science bloggers are saying about it. You'll almost certainly learn that one new study has found some weak effect, and it's probably one we've already discussed here. Really, it will be just one more piece of a large and complicated puzzle that we may never fully perfect. Hopefully, the complete answer is waiting in the wings. Follow me on Twitter and Facebook at Brian Dunning, and follow Skeptoid Media on Twitter at Skeptoid to learn more about this and our other media projects. And please remember to support our show as a nonprofit. It's the only thing that keeps us alive. You're listening to Skeptoid, a listener-supported program. I'm Brian Dunning from Skeptoid.com.